All right, so in this problem, our goal is to find the points of inflection and then to describe the concavity of the function. So to find inflection points, the general technique is to find the second derivative equation and figure out where the second derivative is either undefined or zero. And you're going to study what's going on at those undefined values or those zeros. So we're going to break it up into intervals and see what's going on by looking at the sign of the second derivative. Let's just go through it because it's going to make a lot more sense. So let's first find the first derivative. F prime of x will be, we're going to use product rule because when we have a function times a function, so the derivative of x will just be 1. Keep the second function as is, times x plus 3 plus x multiplied by the derivative of the second function. Remember, this is x plus 3. This is the same as, x plus 3 to the 1/2 and take the square root. So 1/2 times x plus 3 to the negative 1/2. And let me just rewrite it here so you can know what I mean. This is the same as x times x plus 3 to the 1/2. So using power rule times the derivative inside, which is just 1, so you don't have to do anything. All right, now let's find the second derivative. Second derivative, we're going to use just the regular power rule here. This is just using, x plus 3 to the 1/2. So let's do 1/2 times x plus 3 to the negative 1/2 plus, this is 1/2 x is our first function. So we take the derivative of 1/2 x, so this will be 1/2. Keep this as is, x plus 3 to the negative 1/2. Let's put the second part in a group. So we're using product rule, plus keep the 1/2 x constant. And times the derivative of this. So using power rule, it'll be negative 1/2 times x plus 3, negative 1/2 minus 1, so that's the negative 3/2. The derivative of x plus 3 is just 1, so you don't have to worry about anything else. Now let's simplify this because we want to combine like terms. So f double prime of x. Now these go together, these are exactly the same. This is just 1/2 of that plus another 1/2 of that. So it's just going to be 1 full of that. So this will just be x plus 3 to the negative 1/2. You combine those two. And we're going to have plus a minus 1, so this will be minus of 1/4 x. Times x plus 3 to the negative 3/2. Now we want to combine these, so we're going to make them have the same denominators. Let me write them as a fraction. So this is the same as 1 over x plus 3 to the 1/2. I'm going to leave some space between them so I can show you what I'm going to do. Plus, or not plus, minus that. Minus 1/4 x. So 1x on top over 4 times x plus 3 to the 3/2 in the denominator. So same thing. Now, we want to combine these fractions. So remember, we need a common denominator. So we need both of the denominators to be 4 times x plus 3 to the 3/2. So to make this into that, you're going to multiply both the top and the bottom by 4 times x plus 3 to the 1 power, or just 4 times x plus 3, like that. So it'll just be like this, times 4 times x plus 3. And then when you do that, they both have denominators of 4 times x plus 3 to the 3/2, and then so you can work with the top. So 4x plus 12. 4x plus 12 minus x all over 4 times x plus 3 to the 3. And then this becomes just 3x plus 12 over 4 times x plus 3 to the 3. Now we want to find where the second derivative is undefined or where it's 0. So we need to find where f double prime of x equals 0 or undefined. So f double prime will be 0, when you have 3, when you have the denominator as 0, when you have 0 is equal to 3x plus 12. And that means x will be -4. So it'll be 0 when x is -4. Now it's going to be undefined when x plus 3 equals 0. Because remember, if x plus 3 equals 0, that means you're dividing the expression by 0, which will be an undefined. So x plus 3 equals 0. So that means x will be -3. Now, so normally these will be the two values you're going to divide. You're going to set up your table. You're going to set up a table and have intervals on the top, kind of like what we did with the first derivative and where you're setting increasing, decreasing. But remember, you have to double check the domain. So the domain of this function is going to be wherever you can plug these values in, whatever values you can plug x into this equation. Now, remember, if you're taking the square root of x plus 3, that means x plus 3 has to be greater than or equal to 0, because if it's not at least 0, if it's a negative number, you're going to have a non-real answer. So the domain has to be consist of x values that satisfy this. So then that means you take away 3, that means the domain has to be x values greater than or equal to -3. So your domain essentially goes from -3 to infinity. This is your domain. Now, the reason it's important to check that is because if any critical points or any values that you're trying to study lie outside of the domain, you don't even got to do anything. They don't matter, because they're not even valid for the original function, even though they may be valid for the second derivative equation. Remember, we want to study the original function. So if it doesn't fall in here, you don't do anything. And if you look, -4 is outside of there, so you don't have to worry about there. So all you have to do is actually study from -3, which happens to be the undefined value, -3, to infinity. So there's really no intervals. You have to break it up. So we only have to test any value in here. So we want to find second derivative of x. So we'll just find like any value in here. Find what the second derivative of 0 is. So then 0, we just plug it into here. We plug it into that equation here. So f double prime of 0 will just be 3 times 0. So it'll be 0 plus 12 over 4 times 3 to the 3/2. And this doesn't even matter. Like, and you don't have to, in other words, you don't have to find the exact value. You just have to know what the sign is. And this is a positive or a positive. So you know this is going to be greater than 0. So then this is a positive number. So I like these, put a plus, a positive. If you know the second derivative is positive, that means the original function, the f of x graph, is going to be concave up. So it's concave up here in this interval, and since you don't have any points you have to divide it, you just say that the function is concave up on, you know, on its entire domain, and there are no points of inflection. Concave up on -3 to infinity, no inflection points. Remember, inflection points would be where it would change from concave up to concave down or vice versa. And there aren't any, so that's it for that.